Welcome to the second meeting, or meeting one for zero indexing. Is it anyone's first meeting? Anyone who wasn't here? Oh, welcome. I'm Aiden, the president. And so I wanted to remind everyone, I realized we didn't actually talk about this last meeting, at least in person. So I kind of wanted to remind everyone about the kind of schedule for this semester as we're going forward. So the way it's going to work is each month we're going to kind of do like a little cycle. So the first Thursday of each month is going to be a lecture. So for example, today is the first Thursday of September. So I'm going to do a lecture on some computational complexity stuff and some other things near the end, but that's going to be the lecture for today. And the next two meetings are basically going to be sort of open office hours for anything related to competitive programming or really any programming in general, but competitive programming is obviously what we're going to focus on. And those two meetings will be in Enerson 311. So the next meeting is the first one that's going to be in Enerson 311, which is a cool big room that has a lot of tables, good for like collaboration, but not so good for lectures. So that's why we're using this room for the lectures, which will be the first Thursday. And then the last Thursday of each month is going to be like a little mini contest still in Enerson 311. That's going to take up the whole hour. And so it's just going to be kind of see what you've learned, throughout the month. And there might be prizes. I'm not sure. We haven't figured that out yet, but so this information is on the website. The exact date and time of each of these meetings are on the website in the schedule tab. So if you're ever curious, you can check that. And the asterisk right there is the single meeting that will not be from 7 to 8. Unfortunately, because of scheduling jank, that will be from 7:30 to 8:30. But we're going to remind everyone lots of times before that happens so no one forgets. So now to move on to the main topic of today, which is computational complexity, which is probably one of the most important things to know for not only competitive programming, but for programming in general. It's or at least any programming you're doing where speed is very important, which is a lot of programming. And so a lot of this will probably be pretty familiar to people that have taken the Foundations series, like even just Foundations 1 will probably be very familiar. But we're going to work through it using a problem, so hopefully it should be a little bit, less boring and not just me sort of yapping at you. So, okay, so what is computational complexity? Well, in a lot of cases, when we're looking at algorithms, there's a lot of details that we don't care about because algorithms are complicated. They do a lot of different things, and they perform a lot of different operations. And some of those operations are less impactful on how fast the algorithm runs than others. So computational complexity gives us a language for talking about how fast algorithms run without considering every single possible or every single intricate detail of the algorithm. So we usually talk about complexity in regards to functions. So here's an example of a function that takes in value x and returns another number. So in our studies, x is going to be usually an integer, usually a positive integer, because it denotes the size of the input of some kind of data structure. And that size is, well, it's usually positive because negative size things doesn't really make sense. And it's usually an integer, although, we usually pretend that it could be a real number because it makes things simpler sometimes. But this particular function is kind of like a cubic, but there's also this log thing at the end. So it's kind of complicated, but if we look at this function on a graph, oh yeah, so sorry, that's what I just said. we use, well, I guess I didn't say that. The way we use this, computational complexity uses a notation called big O notation. And we group algorithms together based on their most significant growth factor. So I'll demonstrate that with a picture. This is the function that we just saw graphed in red here. And this is what happens when I take all of the terms except for the first one and just delete them, get rid of them. So I'm going to do that right now. It's going to turn blue. So I'll go back and forth between these two a little bit. You can see that there's just a sort of negligible change. It's barely even noticeable. And that's with almost all of the terms removed. So it turns out that this first x cubed term is extremely impactful. It basically determines entirely what this function is going to look like and how it's going to grow as x gets bigger. And so that's what we're interested in discussing essentially, is how do we analyze our algorithms so that we only care about this part, because this part is really the only part that matters. So, so for this example, what we would say is that this function is in O of x cubed. That's how you would say that sentence. So O of x cubed is basically the class of functions that resemble x cubed when you zoom out a lot and you ignore a lot of the details. And so O of x cubed is the class that this function belongs to. And that's a lot simpler to say than this function has time, which is equal to, and then this whole mouthful. So it's a lot more useful, and it's almost, entirely, we don't lose a lot of detail here when we use this notation. So I'll give I think I already said that. I don't know why that's there, but here's a few more examples. Well, the first line is the function we just talked about. But the second line, there's only one difference, is that I've added a constant in front of the x cubed term. And this is another detail that we actually don't care about when we're talking about big O notation. So you can see that it's still an O of x cubed. And the reason is because that constant, in almost all cases, unless it's like a billion or something, is not going to be super relevant for the growth factor again, because the x is usually some really big number. It could be like 1 million. And the 32 just isn't going to change it that much. There are cases where you actually do care about that constant. And sometimes even in applications like credit programming or algorithm design, but at least the definition of this, which we usually just use, does not take that constant into consideration. So this is still O of x cubed. And then this bottom example shows how even more complicated expressions can be simplified a lot. There's 3 terms multiplied together here, and there is kind of a intuition that is built after doing a lot of these, where you kind of realize how you can simplify them down to something like this here on the right. So for example, the first term is 5x plus 3, but really the x is the most important one, so that's why I bolded it. In the second term, 9x squared plus 170x, the x squared is the most important one again. And in this term over here, log of this x squared minus x term, the log is going to basically, logs have a tendency of just sort of removing any detail from the inside, because any x to any power that is inside a log basically just turns into log of x. And I'm skimming over a lot of details. There's a reason that there's a entire OSU class where you learn this stuff, but this is sort of the basic idea. We just remove a lot of the unimportant details and we get something that's a lot easier to analyze and make comparisons with, most importantly. So for example, we can see that even though these bottom 2 expressions are really complicated and it's difficult to tell like which one might be better, when we're looking at them in terms of the O complexity or the big O notation, it's clear that this one on the bottom is slightly better. The log x is really not that big of a factor, but it is slightly better. And so that we might be able to, use that to make a determination on which algorithm we decide to implement. Yeah, thank you.
Thanks.
So, this is a sort of, these are some guidelines for which complexities can be used with which values of n. So earlier I used x, but n is actually more common in this field of study because I don't know why actually. Maybe it's just because n is like usually an integer or an actual number. But anyway, I'm just going to use n here from here and on. And so does anyone know or has taken a class with Nick Painter?
I have.
You have.
Wow.
I kind of stole this from him, slightly modified, but it's a general hierarchy of the complexities. So the top one is the best. O1 means it takes constant time, which means it takes exactly the same amount of time no matter what input you put into it. And the bottom there is O of n factorial, which you can see is labeled fear. And that's because you see O of n factorial, you want to be really scared because that's going to take a long time for any n that isn't like 2 digits, meaning that it's something wrong. So these are kind of rough guidelines for when you come up with an algorithm that has a certain complexity, which values of n they'll actually be okay with. And also you can go the other way, like you see that n can be up to 1 million, you want to get at least something that's like n log n. Yes, but
So based on what you said about constants being pretty negligible earlier, does that mean if you have a function that's O of n plus n, that's fairly different from just O of n?
so in that case, that type of complexity can show up when you have a function that has, or like an algorithm that has more than one input. But I think what you described is similar to like graph algorithms where they have both a number of nodes and a number of edges. And in that case, you can't really remove either of those two. Like you can't really simplify that any further. It kind of depends on the situation, but in most cases, if m and n are like independent of each other, then you might be able to simplify it a little bit. Like you could simplify n plus m over 2 to O of n plus m, but you can't really do any simplification to get only one of those.
I'm just saying, like in terms of runtime, how much different is it? Is it very different at all?
Could you say your question again?
So if you have a function that's O of n and then another function that's O of n plus n, in terms of runtime, are they very different from each
Oh,
other?
I see what you're saying. So n is like a constant.
And it's just like if O of n is a for loop, then you just have 2 for loops, not within each other, just 2 different.
Yeah, that's a good question. So yeah, so if you have, and we'll see kind of examples of that later, but if you have like an n and another n or some other constant, and you bind them together, you get something that is like a constant times n, or at least resembles something like that. And so yeah, it would still be the same complexity. But you do raise a good point that like if you do have a constant, then these aren't quite accurate. I think what these are all rooms of fun. It's more about the order of magnitude than anything. But if you have a 10 next to your n, then something like 5 million might actually be more like 500,000 because the 10 makes it 10 times slower. But yeah, and then I think another helpful rule of thumb, which this is a little bit more general and can work in more cases, is to just assume that there's around 10 to the 8 or like 100 million operations per second. That's a pretty, not pretty accurate, but at least in terms of order of magnitude, that's pretty close to what most online judges will run, or even most computers in general. And so that can be used a lot for if you have a function that you figured out using the unnotation simplification housing function, if you plug in the maximum n into it and it's more than that by a lot, then you should probably look into trying to make some more optimizations.
Mhm.
All right. So to demonstrate this, I'm going to go through like an example problem. And it doesn't really, I don't really remember how we came up with this example problem, but it's a good, I think it's a good example because there's a lot of different ways to solve it and they have different speeds. So, it's a very abstract problem. What we're interested in, I can actually take over the.
Yeah, go
it's
for
a
it.
little bit more, yeah.
Yeah.
So, if we take two adjacent entries in this list that we're given as input, we can find the absolute difference between the two. And so that's basically like, we subtract them, but we make sure that's positive. So the absolute difference between 4 and 9 is 5, and it would be the same if it was the other order. And so what we're interested in doing is looking at all of the entries. So for example, again, 9 and 2, the absolute difference would be 7. And we look at that difference between every pair of adjacent entries. And what we do with those numbers is we add them all together and we get this total here, 66. So one thing we're allowed to do is to change the order of these numbers in any way that we'd like. So for example, I can make this permutation. I can move the 2 over and then move the 4 to the right and swap the position of those two. And if we did the same process with these numbers or this order of numbers, we get 56, which is a lower number. And so that's actually what we want. We want to figure out in what way of rearranging these numbers can we get the lowest number from this process, basically. So what?
Just
Yep.
ascending order.
That's a very good idea. But let's start with maybe a more immediate approach that you might come up with if you were working on this problem. So the first, at least, not the first attempt, but maybe the first thing that you probably think of or will think of as you get better is the brute force solution to a problem. And brute force is essentially like the bare minimum way of solving the problem that actually works. So in this case, we're interested in figuring out which of the permutations lead to the smallest cost. That's what I'm going to call that. Sum is the cost of the permutation. And the most direct way of doing that is to just check all of them. So we initialize a minimum, and then the minimum should actually be like infinity, I think, but it's not that important. And then we check each permutation of L, we compute the cost, and if it's less than the minimum, then we set the minimum. So we essentially go through every permutation of the list, and we figure out which one has the smallest cost. Okay. So any objections to this algorithm? Yeah.
If the min starts at 0, wouldn't it always, minimum always be 0 then?
Yes, so that's a good observation. I think that should be infinity. for
Yeah.
that to work, or at least some really big.
The
number.
max value for your data.
Yeah,
storage
int
there.
dot max value or whatever the equivalent is. But that's actually just a typo, but good catch. But there's it actually is correct, but there's a bigger issue here. Let's say if our list is 20 elements long, does anyone want to wager a guess to how long this will take? Just 20 elements.
A lot, like 20 factorial maybe?
Yeah, exactly, 20 factorial. It's actually going to be even a little bit longer than that because every time we compute the cost. So this is going to take n times n factorial is the running time of this function. And n factorial, if you're not familiar, is the number of permutations of any given list, basically. And it's a notoriously fast growing function. It grows very fast. So turns out if we just are using n equals 20, then yeah, thank you. Here's Python telling us how many iterations roughly that would, or like how many operations that would be. And that's like a really long number. That's the second number there. This is how many digits it has approximately. So 19 digits. So it's roughly 4 with 19 zeros after it, which is really big. That's, remember, our rule of thumb says that 1 with 8 zeros after it is what we can do in 1 second. So running this algorithm for n equals 20 will take around 300 years, which is beyond the lifespan of most people. So that doesn't seem like a good idea. So we have to do a little bit better than this, of course. Here's one thing you might realize after staring at this problem for a little bit, is that if you have a situation like this in the list, these are just 3, numbers that are next to each other in the list, and you have this sort of local maxima or minima where it goes up and then it goes down. This can actually be reduced by swapping it, making it more straight looking. So you see we have this like little kink for thinking about the height of this graph as being the value of the number. And I tried to demonstrate why this is better, but I don't know if I was successful in doing so. But you can see if we make it more straight, the difference between the adjacent entries is going down just a little bit. This red line on the right actually stays the same, but the other one gets smaller. And so one idea might be, what if we just keep trying to do this over and over again, keep swapping elements that have this, kink in it. And so that's the idea for the second attempt at a solution, which is just called swap adjacent. So that's exactly what we do. I'm going to focus on the inner 2 lines first. We look at each adjacent set of values x and y, and then if x is bigger than y, then we swap them in the list. We're just changing the order of the list. If we see a place where we have this sort of up and down, we fix it by swapping them. And this will always make the list better, or at least won't make it any worse. And so, in theory, doing this over and over again will make the cost smaller. So it's not entirely clear, or it's not entirely obvious, but we actually only need to do this whole process n times. And it'd take a little bit to explain, but I think it's better here to just say, trust me on this one. It's because after doing this process n times, you're going to have something that's completely straight. It's going to look like a upward curve, monotonic curve. And by the end of that, you will have minimized the total cost of the list, or of the permutation, I should say. So, thanks. So to figure out how long this takes, we can first see the inner loop, the one that I described, does n-1 swaps, because it does each adjacent pair of values, but it doesn't it only ends at the second to last one. So it's actually only n-1, but remember, because we're ignoring the details, that's O of n swaps. And that outer loop, well, we literally say do it n times. So it's going to run n times, and so n times the n is n squared for those first 3 lines. And then this last line, the return statement, we compute the cost, which we can do just by going through the array once. And so that takes n time. And if we add these together, we get something that's in O of n squared, because remember here that n is much smaller than the n squared. The n squared is the dominant factor, or the dominant term, I should say. But yeah, if that function looks a little familiar to anyone, that's because it's literally just bubble sort, going through a whole array, doing a bunch of swaps. So that's a very inefficient way to sort. And if we're trying to get a sorted array, then we might as well just do an efficient sorting method. So that's attempt 3, which is literally just quick sort it, and then return the cost. So. The quick sort, which if you're not familiar with, it's a recursive, like a divide and conquer sort. It takes n log n time. And again, computing the whole cost just takes n time. So when you add those together, you get something that's O of n log n, which is really good. That's a lot better than n squared. Because you're replacing an n with a log n basically, and log n is like basically flat for anything that's, below a billion. So that's a really good improvement. But there's actually a way that we can do a little bit better. I want you to try to crowdsource this. Crowdsource this one. Yeah, that's that.
And you just do the max value minus the minimum value.
Yes, exactly. So I tried to, again, demonstrate this with a pictograph. So this is our straight sorted, our sorted list, or our sorted permutation. And you can see that what we're computing, the sum here, the cost, is the sum of all these little segments. Because we're computing the difference between the adjacent segments. And so you can go port one. What we're basically computing, if we just think of them all end to end, is the difference between the smallest one and the biggest one. That's just this big red segment. So attempt 4 is just the maximum minus the minimum. And we can actually compute those two values faster than we can sort the array. And so that's exactly how we do this. I see we have the correct bounds here, hopefully. And so we go through the whole array, we update the max and the min accordingly, and then we just return the difference between the two. Now. Okay. And then this takes O of n because the for loop just goes through we only iterate over each x in L once. So we only do n operations basically, or at least some constant times n. And so this is O of n, which is better than O of log n, if only by a little bit. Now, attempt 5. Can we do any better than O of n? Any ideas? So it turns out that no, we can't. What we have is actually the best we can possibly do. And we can do this by considering an argument where when we're creating this algorithm, any algorithm that claims to solve the problem, step 1 is to just read in the inputs. We have to read in the entire list that we're going to be, commuting. And that alone takes at least n operations. Like we have to read in each number, we have to do at least n, cins or next ints or whatever you do to get input. And so there's literally no way to do any better than O of n because we have to do at least n things. That's what this omega notation represents, at least n things. And then we also have to do, the programming to make sure it gets the right answer. So there's no way to get any better than O of n in this case. And this happens to be the case for a lot of competitive programming problems because a lot of problems you actually have to get input. So, in summary, we started with something that was really bad in the fear category. But then we slowly improved it over 3 iterations, and we got to something that was as best as we can possibly do. And so a lot of your, this is a very sort of contrived example, but this tends to be how the process of solving problems goes. You start with something that you know is probably not great, but at least solves the problem, and you slowly figure out how to make that faster by being more clever. So that was the main sort of content part. Hopefully, if you already knew how that worked, that was at least somewhat interesting. And the last part of the lecture, I kind of just wanted to give a brief, I don't know, just a sort of, view of the landscape, a rough, idea of what other things there are to learn. And I guess just get you excited about the things that you might be learning in the future. And hopefully most of these things are things that we're going to cover, in this lecture at some here. So divide and conquer algorithms, we talked about one earlier, quicksort. But the way that they work is like splitting the problem into a few pieces, usually 2, maybe 3 or 4, and solving those pieces recursively and then combining the results together in a way that yields a correct answer. So quicksort is an example. Binary search, I think it's technically considered divide and conquer, although it's one of the most simple versions of divide and conquer. And I just wanted to mention the fast Fourier transform is a very interesting algorithm that can be used for doing a lot of weird things like multiplying numbers really fast or multiplying polynomials. It shows up in some cases at the very high level, but yeah, it's pretty complicated. Involves a lot of like complex numbers and stuff, but I don't really know numbers yet. But graph algorithms are algorithms that operate on graphs, which are these structures that have nodes and edges. So you can use graph algorithms to answer questions about graphs, like whether there's a path between 2 nodes, or what's the shortest path, what's the widest path, which is like the path with the minimum largest edge, and there's a lot of other stuff like flow networks. Graph algorithms go very deep, and yeah, there's a lot, surprisingly a lot to this very simple condition. Dynamic programming, which I was talking about with earlier, but it's more of a technique than a specific algorithm for solving problems that at first look like they're really inefficient, like exponential time, but you can solve them more efficiently by reusing some of your work. Here's actually an example of famous or infamous problem, I guess, however you look at it, problem called edit distance, which is figuring out what's I'm talking about. Figuring out like a way to change one string into another with the minimum number of operations. And then that's the Fibonacci numbers down there. But it'll make more sense when we talk about that. And then I just kind of grouped together all this cool math stuff because this also does not nearly give enough. Putting them on this one page makes it seem like something that you can learn in the same amount of time you can learn like graph algorithms. But there's a lot of stuff here I just honestly don't know that much about it, and also I don't know if it would be that interesting to like go into detailed lessons. But there's a lot of interesting math algorithms you can do. Number theory is the study of divisibility, like prime numbers and stuff like that. Combinatorics is basically how do you count things fast. Game theory is like kind of exactly what it sounds like. How do you optimally solve mathematical games? Here's an example of one. This is called NIM. And Sprague-Grundy theorem is actually related to showing that most games are just this pile of matchsticks over here. And then there's probability, which quicksort is actually lies under this because it's randomized algorithm, and geometry, algorithms for operating on geometric structures, figuring out things like area and distance and interesting stuff like that. So that is the end of the lecture. Last week we had a contest, but I think because we want to try to encourage people to try different websites, programming websites, and a wide variety of types of problems, instead of contests from here on out, other than the contest at the end of the month, we're going to compile a list of problems for the month that's related to the stuff we talked about in the lecture. Now, the reason this lecture is kind of an exception because we didn't talk about a topic in particular. We talked about complexity theory, which is important, but we didn't talk about any particular lecture or any particular topic. So this first month is mostly just going to be our list of problems is going to have problems that are more foundational and are sort of simpler problems, I guess you could say, or problems that don't involve any of the stuff I just mentioned in the past 5 minutes. Like they don't involve dynamic programming or graph algorithms are more like, figuring out how to use.
Found some bunch to get.
Yeah, they haven't, yes. But problems that involve just using data structures and collections and just early, figuring out how to manage the input and output and stuff like that, so. Yeah,
Is there like a schedule on the competitions or is that like specific?
so the competitions, you mean like ICPC? Like.
Yeah, like the different competitions you guys attend, when do those start? Or
Yeah.
is it like a tryout, like where you release them?
So there's, for ICPC, the tryouts is basically a contest we run called NAQ, which is the North American Qualifiers. And basically anyone can attend the contest, and whoever does the best in that particular contest, we send to the next stage. So that happens, I think, last
It was October,
Yeah.
early October, I think.
early October, something.
Don't
like
quote
that.
me on that, but I think it's early October.
Yeah.
We'll send more details out as we get more ourselves, but.
Yeah, we're also like kind of bad at updating us. But yeah, we will definitely inform you as soon as we have, information about them.
Yeah,
So soon I'm going to post, what we currently have is like a document of problems. It's probably going to grow in size as the month goes on because there's not enough right now. But it should be at least enough to like kind of get you started and have something to do for the remaining 20 minutes. So I'm gonna do that right now.
yeah, as always, feel free to ask us questions here or on the Discord. We're generally fairly accessible, so if you guys run into issues with anything, whether you're just trying to figure something out or can't quite get the intuition, feel free to talk to us and we'll try to help you out.